Hi guys, welcome to this set of video lessons. These videos are all going to follow along with the notes that come out of your textbook from Chapter 5, Section 8. And all through Chapter 5, we've been dealing with polynomials. And now what we're going to do is sort of come to the granddaddy conclusion of polynomials, going back to that very, very important factor theorem and just sort of amping up those problems and really kind of driving home this idea of what you can do with a polynomial and finding the roots or zeros of that polynomial using several of the theorems we've found here in this chapter. But before we jump into that, let's take a look at the objectives or learning targets you guys are going to need to keep in mind as we work our way through this set of notes. First, you're going to want to be able to identify the possible rational zeros of a polynomial function. We'll do that using the rational zeros theorem. We'll get to that in just a second. Then you'll need to be able to find all rational zeros of a polynomial function, which means that not just all possible, but eliminate the ones that are not actually rational zeros so that you get it down to just a list of the actual rational zeros of a polynomial. And again, we'll get to that in just a second. Now, before we jump into this rational zeros theorem, I quickly just want to refresh your memory on what we've already done with the factor theorem. So, previously in previous sections, I have given you a problem like this. In fact, this is a problem off of an earlier set of notes in this chapter. I give you a polynomial, and I ask you to find all of the remaining factors. And of course, once you know the factors, you can find the zeros. We'll do that. All the remaining factors of the polynomial given x plus 1 is a factor. So remember, the way that we did this was very, very simple, and actually we'll just work through it because they're not that difficult. It's actually a pretty easy problem. You know that x plus 1 is a factor, so you need to do synthetic division to find the reduced polynomial. We go x plus 1 equals 0, so x is equal to a negative 1. I'm going to do my synthetic division with a negative 1, which goes inside the box. Check to make sure I don't need any placeholders. 3, 2, 1, 0. I'm not missing anybody, so I don't need to add any placeholders. It's going to be a 1, a 4, a minus 7, and a negative 10. Bring down that first coefficient. Negative 1 times 1 is a negative 1, which leaves me with a 3. That's going to give me a negative 3, which gives me a negative 10. Negative 1 times a negative 10 is a positive 10. And yep, I get that remainder of 0, which I know that I should. If I didn't get a remainder of 0, you know you did something wrong, because I tell you x plus 1 is a factor. You'd better get a remainder of 0. So now here's what I can do. I can take that polynomial I was originally given and rewrite that polynomial as my two factors, x plus 1, which is the factor I was given, and my reduced polynomial. It was third degree, so this will now need to be a second degree, x squared plus 3x minus 10. Now what we do is we use, Now what we do is we use the other factoring methods we've learned in this chapter, see if I can factor that guy, and it does look like it's going to factor into two binomials, so we'll quickly do that as well. It's going to be x, looks like it's going to be plus 5, and x minus 2 would be my other two factors. X times x gets me x squared. Positive 5 times negative 2 gets me negative 10, and a positive 5 plus a negative 2 gets me the positive 3. So these two numbers need to multiply to a negative 10. These two numbers need to sum to a positive 3, and that's how I do it. So I asked you to find the remaining factors, which you did. Here they are. But further than that, I could have you find the zeros, right? All you would need to do is set this guy equal to 0. So now I want to know, where does it cross the x-axis? In which case the zero product property lets you split these guys up. and I get exactly what we knew we should get. It was a third degree polynomial, which means I should get 3 zeros, and I do. X equals -1, x equals -5, and x equals 2. That's where the polynomial would cross the x-axis. Now, why refresh your memory on these kinds of problems? Oh, sorry, hold up. Slide all this down. Sorry. Get all this out of the way. I want my previous problem. Sorry, I got stuff sliding around all over the place. There it is. So previously, right, these were the kinds of problems we're going to do. In this section of the notes, here's what we're going to do. We're going to do these exact same problems where I will give you a polynomial. I will ask you to find all of the factors of that polynomial. But in this section, I will not give you that piece of information. This is it. This is all you're going to get. You'll get the polynomial. I'll ask you to find the remaining factors. I may even ask you to find the zeros, meaning you'll set it equal to 0 and solve those factors for the actual x-intercepts. But I am not going to give you a factor from which you need to work, which means what we're going to do in this set of notes is first give you a method for finding these factors. Then once you know what those factors are, you'll have to go through systematically and check them until you find one that works. Then once you've found one that works, the rest of the problem will be exactly the same. So I'm really excited to get started on this. Let's head back to that previous page of the notes, the front page, and here we go, jumping right into this, the rational zeros theorem. Here's how we're going to find those factors. We're going to use this rational zeros theorem to help you find possible rational zeros of the polynomial. Here's what you're going to be doing. You are essentially going to be, let me highlight for you the important stuff. All we're going to do you're going to generate a list of possible real zeros for any given polynomial. Possible real zeros. Not all of them are going to be real zeros. We're going to have to work our way through and check them to find one that does work. But you'll be creating, this theorem allows you to create that list, and then once you've got the list, we'll work our way through it to find one that works. So here's the way it works. I give you the crazy long book definition. Not really important. It'll make a lot of sense when we do an example problem. Here's the big stuff. Really all you need, you put your polynomial in standard form. That means descending order. And what you need are two numbers. You need the leading coefficient, which is an, and you need the constant at the end, which is a naught. I call them, in the notes, I call them P and Q, where a naught is P and an is Q. That's just kind of the terminology that your book uses, but other textbooks are going to use other letters. So the constant between textbooks is this. Don't really worry about the P and the Q. All you need to know, a naught and an, because every textbook is going to use that notation. So a naught, the constant at the end, an, the leading coefficient. Those are the only two numbers that matter. Here we go. You'll see what this looks like right down here when we do an example problem. So what I need is I need a naught and an. A naught, oh, that's a terrible a naught. Hold up. There we go. A naught is equal to the constant at the end of my polynomial, which in this case is a 3. Don't worry about the sign. You don't need the sign. It's a 3. And then I need an, which is the leading coefficient. In this case, that's a 4. Now what you're going to do is find the factors. You need all the factors of those two numbers. So the factors of 3, which is actually a very short list. I could do +1 and +3. Positive 1 times a positive 3 gets me 3. But also I could do a -1 and a -3, which also get me 3. Or I could do a +1 and a -3, which gets me the -3, which I was given, or a -1 and a +3, which gets me the -3, which I was given. Anyway, ±1, ±3. And in fact, every time you write factors, you'll need the plus or minus. It'll always be plus or minus, and then the factors of that number. Here we go, let's do this one. 4. I need all of its factors. And again, the factors of 4, plus or minus 1, plus or minus 2, and plus or minus 4, right? Those are going to be my factors of 4. Again, I can multiply those guys together in any combination and get 4. Okay, so here's what you're going to do. Your list. Remember, what we're doing is we are writing a list of all possible rational zeros for this polynomial. Here's the list. The list is going to be a naught over an, and you're going to systematically work your way through the factors to get all possible combinations. Just like with Descartes' rule, same thing here. We want all possible combinations of the factors to write our list. So the first one would be plus or minus 1 and plus or minus 1, which would be plus or minus 1 over plus or minus 1. Okay? And then I'd have plus or minus 1 over plus or minus 2. Okay? And then I'd have plus or minus 1 over plus or minus 4. Okay, I've gone through the 1 and done it with everybody, right? A naught over a n. These guys always go in the numerator. These guys will always go in the denominator. We do the next one. Plus or minus 3 over plus or minus 1, right? Just systematically work your way through so that you don't forget any. Plus or minus 3 over plus or minus 1. And then plus or minus 3 over plus or minus 2. And the last one, plus or minus 3 over plus or minus 4. Now all we're going to do is just simplify this list, because I got a whole bunch of stuff running around here, right? 1 divided by 1 is just 1, so that'll be plus or minus 1. 1 divided by 2, I can't reduce it, it's 1/2. I don't need all those plus or minuses though, I can just simply put it out front, plus or minus 1/2. And then again, 1/4, there's no way to reduce that, I just bring the plus or minus out front, so plus or minus 1/4, plus or minus 3 divided by 1 is just 3. 3/2, it's 1.5, there's no way to reduce it, so it's going to be plus or minus 3/2. And the same thing with 3/4, plus or minus 3/4. There you go, guys. That is the rational zeros theorem, and here's what it says. If my polynomial has a rational zero, if it has a rational zero, that zero is somewhere in this list. Now, I know my polynomial is a second degree, which means I only have 2 zeros. 2 zeros. Look at how many numbers I have in this list. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 12 possibilities. I don't have 12 zeros. I only have 2. And they could be imaginary, right? So it's possible that none of these are actual zeros. But if I have a rational zero, if this polynomial crosses the x-axis, it's gonna be one of these guys. All right, it's gonna be one of these guys. Head on over to the next page of the notes. We'll practice the rational zeros theorem a few more times. I'll meet you over there.